Hi, in this video I'm going to show how to generate C code from a MATLAB script that implements an algorithm to detect cells in images using the image processing toolbox. So what it's going to do, the algorithm is take an image like the original cell image, and it's going to segment it and then overlay it to highlight the pixels that correspond to the full cell. Okay, so let's take, this is the example that I'm doing. I'm going to open the live script. Okay, so the live script recommends using the MATLAB Coder, although I'm not gonna use it because I find it easier if you have a test bench that calls the algorithm. This algorithm that we're gonna use that uses the image processing toolbox functions, because MATLAB Coder needs to infer the types for the entry point of the function. So instead, I'm gonna use the command line, which I find more convenient and you have more control over it. Okay, so let's first you have to make sure that you have the right compiler. I'm using Visual Studio 2017. If you don't have it, install either MinGW or Visual Studio, and once you install it, run this command and just click on it to just set it as your default compiler. Okay, so let's load the image. Let's take a look at how the original cell looks. Okay, so this is what we want to detect. Now let's run the script just to take a look. Let's put a breakpoint just to understand an overview of how it works. Okay, so first we're gonna apply an edge detector with the option of shovel. There are other options, and with that we're getting the threshold because the example was not satisfied with the default threshold. So what it's gonna do is getting the threshold divided by 2, multiplying by 2 like this. Now this gets another threshold, a lower one, and then apply again the shovel filter on the original image to get the edges. Now let's take a look at how are the edges. So yeah, we got the edges, but they're broken, they're incomplete. We are not really caring about the edges, but the whole segment of the cell. That's what we want. Okay, so for that we're gonna delete the image to the make a I mean to try to form the full segment. I mean making the larger the dots, I mean the pixels, and that way we grow the edges and try to create the full image. Okay, so for that we're gonna use a structural element. So we're gonna use the option of line, and with that we specify the length. This is the length and the angle, and you can see that from the help. If you type help, you can see. So you have, yeah, this is the line, the length and the degrees. So we have a vertical and horizontal structural element, and let's see at the neighbor. This is gonna create a kernel for the IM delay morphology operation. So let's take a look at it. So this is a vertical line and the other one is a horizontal line. So we're gonna fit those two into the image process toolbox delayed operation, and let's take a look at how the image looks. And the pixels are delayed, so the pixels grow, and we're taking a step towards making the full segment of the image. And then still there are holes, so we are going to use the IM field, another morphology based operation, which underneath uses delayed and erode, a combination of those to basically fill the holes in the image, and that's the option that we indicate in here. So let's take a look at how that looks. Okay, so we're getting there, and we are only interested in the complete cell, so we're gonna clear the incomplete cell in here by using this other function. So now that is gone, we have this cell alone, so we have to clean this out by eroding the image. Now we're going to use a diamond structure element. Let's take a look at how it looks. So we specify the size of 1, so that's why we got a 3 by 3 kernel that is being passed into the morphology erode operation. Okay, so let's take a look how it looks, and now we have what we wanted, the perfect segmented image. and now we're gonna overlay it to see how it looks on top of the original image, just by passing the original image and the segmented image, which are both of the same size. Oops, that's not what I wanted. Okay, yeah, so it looks fine. So now let's generate code for it. For that, we're gonna create a MATLAB Coder configuration, which is created with coder config, and we indicate that we want a MEX. The advantage of the MEX is that you can easily run it in the MATLAB desktop. And now we're going to use the cogent command, and we have to parse the arguments that you would pass to the function if you execute it like this, the same argument. And this is needed so that MATLAB Coder can infer the types for the inputs of the generate C function. And this is the name of the function that we're going to use. The cogent function is exactly the same as the original one. The only difference is that we put this comment in here with indicating that the function should be ready for cogent things. It is not true. We have to make some modifications, but we will see in a moment. Also, I'm passing this optional parameter that is a relatively recent feature of MATLAB Coder to preserve dimensions in generic code. Because without that feature, if you have matrices or tensors in generic code, the arrays are going to be flattened, so you're going to get vectors for them. But we're dealing with matrices in here, which are two-dimensional, and it's convenient to see the generic code as matrices rather than vectors. And also, it can help with some optimizations. It can help SIMD and other things. So it's more convenient to have that flag, especially if you're dealing with matrices or tensors. Okay, so let's generate code. And this should throw an error because IMShow is not ready for code generation, and really we don't need it for the algorithm. That's just for visualization, so we just can comment it out. Okay, so I'm gonna pause because okay, I'm finished with commenting out this command. So let's try it again. It's gonna complain saying that code generation does not support object arrays, and these are the object arrays that they do not support. So we're gonna break it down into. Let's just call one at a time, one after the other, and the output of the first is the input of the second. Okay, now it should be able to generate code for it. Okay, and the generate code is gonna go to the cogent folder within MEX in here, and the entry point is gonna have the same name. The file has the same name as the function, so this is the entry point. And also within the file, the entry point is also the name of the function. So it is this one. And you can see that the input, because we are preserving dimension, we get a matrix as an input and a matrix as an output. And we can, just by looking at the code, we can see the morphology operations around, and you can see that everything is ND. We have nested for loops, which is very nice, very for viewing and also for optimizations. Okay, so now that we generate code for that, we're gonna run it to see if it is doing the right thing. I'm gonna clear the output, the previous output, just to make sure that it's working correctly. Okay, now let's run it. But we are using the cogent version, and in addition to that, when you generate the MEX file, it automatically appends this suffix. You can use the negative O option to indicate the output name, but by default this is the output name for the MEX. So let's run it, and now we can overlay it again just to see if we did things right. Okay, so the generated MEX file worked. This is all. Thank you for watching.